Security teams get into trouble when they treat AI systems like they are too new or too strange to fit into normal vulnerability management, because attackers do not give you a novelty discount. The reality is that an AI deployment is still software, still dependencies, still services, still data flows, and still changes that can create weaknesses. The difference is that the weak points can hide in more places, like model supply chains, model serving layers, plugins, connectors, and the libraries that handle tokens, files, and parsing. Tracking AI vulnerabilities is the discipline of noticing those weak points early, understanding whether they apply to your environment, and taking action before they become real incidents. A key part of this discipline is learning how vulnerability information is published and shared, and how your organization can turn that information into decisions. By the end of this lesson, you should be able to describe how CVE workflows work, how advisories fit in, and how exposure management turns raw vulnerability news into practical risk reduction. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. The term Common Vulnerabilities and Exposures, CVE, refers to a standardized way of identifying publicly known vulnerabilities so people can talk about the same issue using the same label. That matters because without a shared identifier, one vendor's blog post, another vendor's patch note, and a third-party scanner report might all be describing the same problem in different words. In everyday operations, CVE acts like a tracking number that lets you connect the dots across tools, tickets, and teams. For AI systems, that same idea applies, but the surface area is broader than learners often expect, because the vulnerability might live in the model-serving framework, the container image, the web service that wraps the model, the authentication layer, the document parser, or the plugin that connects to an internal repository. Beginners sometimes assume vulnerabilities are only about the model, but many AI risks are actually vulnerabilities in the components that move data into and out of the model. When you track CVE information consistently, you reduce the chance that a fix is missed simply because the issue was described differently in different places. A CVE workflow is the path an issue takes from discovery to public disclosure to patching and mitigation, and it usually includes multiple organizations and steps. Someone finds a vulnerability, such as a flaw that allows unauthorized access, remote code execution, or information disclosure, and they report it to a vendor or to an organization that can assign a CVE ID. The vendor investigates, prepares a fix, and coordinates disclosure so defenders have a chance to patch before attackers widely exploit it. The details of the workflow can vary, but the basic pattern is stable: discovery, validation, identification, publication, and remediation. Understanding this pattern matters because it explains why information can be incomplete at first and then become clearer over time. Early reports might not include full technical detail, but they may be enough to trigger protective action, like disabling a feature or limiting exposure. For AI systems, this is especially important because the vulnerability might impact a popular library that many products quietly depend on, so early awareness can prevent widespread exposure. Within this ecosystem, organizations called Common Vulnerabilities and Exposures Numbering Authorities, CNA, play a key role by assigning CVE identifiers for vulnerabilities in products they cover. You can think of a CNA as an authorized publisher of tracking numbers, which helps scale the system so every issue does not bottleneck through one central authority. The practical impact for a security team is that you will see CVE IDs come from many sources, including large vendors, open-source projects, and security organizations. This matters for AI because many AI stacks rely heavily on open-source components, and open-source projects often handle disclosure and patching in their own way. A beginner misunderstanding is assuming that if a vulnerability is real, it will always show up immediately in the same place with the same level of detail. In reality, you may first see an advisory, then later see a CVE ID, and then later see scanner signatures and exploit chatter. A good tracking process is built to connect these signals, even when they arrive at different times. Advisories are the narrative layer of vulnerability information, and they are often where the actionable details live. A CVE ID tells you what to track, but an advisory often tells you what versions are affected, how the vulnerability can be exploited, what mitigations exist, and what patches are available. Vendors publish advisories for their products. Open source maintainers publish advisories for their projects, and third parties publish advisories when they coordinate disclosure or analyze impact. In AI security, advisories are particularly valuable because they may explain how a vulnerability interacts with real-world AI deployments, like whether a flaw is reachable only when a certain feature is enabled, whether it affects a default configuration, or whether it can be exploited through typical API usage. That context determines urgency, because a vulnerability that exists in a library you use might not be exploitable in your specific deployment path. Tracking advisories alongside CVE IDs helps you avoid two common mistakes: panicking about issues that do not apply, and ignoring issues that do apply because they sound too niche. Exposure management is the discipline of turning vulnerability knowledge into a clear picture of your own risk, and it is different from simply having a list of CVE IDs. Exposure management begins with inventory, because you cannot know whether you are affected if you do not know what you run. For an AI system, inventory includes not only the application code, but also the model-serving framework, container images, orchestration layers, plugins, connectors, and any libraries that handle user input, file parsing, network calls, or data retrieval. It also includes versions, because vulnerability impact is usually version-specific. Once you have inventory, you map vulnerabilities to assets and then to exposure conditions, such as whether the vulnerable service is internet-facing, whether the vulnerable feature is enabled, and whether compensating controls exist. This is where beginners often level up, because they learn that vulnerability severity is not the same as your risk. Your risk depends on exposure, privileges, and reachability, which are all choices you can influence. AI systems add a twist to classic vulnerability management because some failures are about insecure integration rather than a single bug in a single component. For example, an issue might be described as an authentication bypass in a gateway, but the real exposure depends on whether that gateway is the only path to the model or whether direct access exists elsewhere. Another issue might involve a document parsing library, but the real exposure depends on whether your system accepts user uploads or only processes curated documents. This is why the phrase exposure conditions matters so much. A vulnerability can exist on paper, but if the vulnerable code path is not reachable, the practical risk is lower, at least until the system changes. At the same time, a seemingly small vulnerability can become serious if the vulnerable component sits on a sensitive boundary, such as a service that holds credentials or a connector that can reach internal repositories. When tracking vulnerabilities in AI, you continuously ask how the bug intersects with data flows and privileges, because those intersections create the real blast radius. A disciplined workflow for tracking AI vulnerabilities usually starts with intake, meaning where vulnerability information enters your process. Intake might include vendor advisories, open-source security advisories, vulnerability databases, security mailing lists, and internal scanning tools. The key is that intake should be consistent and monitored, not random, because attackers do not wait for you to stumble across the news. After intake comes triage, where you classify the issue based on relevance to your environment, potential impact, and exploitability. For AI systems, triage should include questions about whether the model endpoint is reachable from outside, whether the component runs with elevated privileges, and whether the vulnerability affects confidentiality, integrity, or availability. Then comes assignment and tracking, where you create an internal record that links the advisory, the CVE ID if present, the affected assets, the owner, and the planned remediation. The final step is closure with evidence, because you want to know not only that you plan to fix it, but that the fix actually reached production. Versioning discipline is a quiet hero in vulnerability tracking, because without it you cannot confidently answer the question, are we affected? If you pin versions of model-serving components and libraries, you can map advisories to your environment quickly. If you let components float to latest without tracking, you may not know what changed last week, which makes both risk assessment and incident investigation harder. For hosted model services, Versioning can be trickier because the vendor may update behind the scenes, so your tracking process should include vendor communications about model updates and platform changes. For self-hosted stacks, versioning often means maintaining a software bill of materials, which is a structured record of components and versions. Even when you do not use that formal term, the principle is the same. Keep a reliable inventory. Beginners sometimes think version tracking is just paperwork, but it is actually the foundation for fast, accurate response. When a high-profile AI-adjacent vulnerability drops, speed matters, and speed comes from knowing exactly what you run. Patch strategy is the operational side of vulnerability management, and for AI systems it needs to include both software patches and configuration mitigations. Sometimes the best immediate action is not a patch, especially if a patch is not available yet. You might temporarily disable a risky feature, restrict network access, tighten authentication, reduce privileges, or add additional validation around inputs. These mitigations can reduce exposure while you wait for a formal fix. At the same time, mitigations should not become permanent by accident, because temporary workarounds can pile up and create hidden complexity. A solid patch strategy defines how you apply fixes in stages, such as testing first, then limited rollout, then full deployment, with monitoring at each step. It also defines rollback discipline, because an update might change model behavior or break integrations in ways that matter for safety. Tracking vulnerabilities is not complete until you can patch or mitigate reliably, and doing that reliably requires a process that is calm and repeatable even when the news cycle is loud. A special challenge in AI vulnerability tracking is distinguishing between a vulnerability and a misuse risk, because both can lead to harm, but they are managed differently. A vulnerability is typically a flaw in software that allows something unintended, like unauthorized access or code execution. A misuse risk might be something like prompt injection or data leakage through weak policies, which is not always a single patchable bug. Both matter, but the workflows can differ because vulnerability tracking often maps to patches and version updates, while misuse risk tracking maps to design controls, monitoring, and policy changes. The reason this distinction matters is that vulnerability channels like CVE are not guaranteed to capture misuse patterns cleanly, and misuse patterns may evolve faster than disclosure cycles. A mature exposure management program tracks both, but it labels them honestly so teams choose the right response. Beginners sometimes expect every AI problem to have a CVE number, but many important AI risks are systemic and require layered controls rather than a single fix. Communication is also part of secure tracking because vulnerability management is a team sport. Security teams, engineering teams, and operations teams all need a shared understanding of what an advisory means and what the plan is. Clear communication includes the affected assets, the exposure conditions, the mitigation or patch plan, the owner, and the deadline. It also includes why the issue matters, stated in a way that matches the business impact, such as risk of data disclosure, risk of service outage, or risk of unauthorized action. For AI systems, it can help to describe the potential blast radius in terms of data access and tool permissions, because those details make the risk concrete. Another communication habit that matters is documenting decisions, such as why an issue was deemed not applicable, because future changes might make it applicable. When you track vulnerabilities over months, not days, that paper trail prevents repeated confusion and helps newcomers understand what happened before they arrived. Monitoring closes the loop by letting you see whether your fixes actually reduced risk and whether attackers are trying to exploit known issues. After a vulnerability becomes public, attackers often scan for it, especially if it is easy to exploit and affects common components. Monitoring can include watching for unusual requests to model endpoints, spikes in error patterns, or unexpected file upload behavior, depending on what the vulnerability involves. It can also include checking for anomalous outbound network calls from model services if the vulnerability could lead to code execution. For beginners, it is enough to remember that patching is not the end. Verification is the end. Verification means you confirm the vulnerable version is gone, the mitigation is active, and the service behaves normally. Good monitoring also supports learning, because it shows where your exposure truly was and whether your assumptions held. Over time, These lessons improve your design decisions, like tightening boundaries and reducing unnecessary features, which lowers your vulnerability exposure before the next advisory arrives. When you put everything together, tracking AI vulnerabilities is a repeatable cycle that turns external information into internal action. You watch for CVE IDs and advisories. You connect them to your inventory, and you assess exposure based on reachability, privileges, and data flows. You then choose the right response, whether that is patching, configuration mitigation, feature restriction, or a temporary shutdown of a risky interface. You document, communicate, and verify, and you treat the system as something that changes, not something you secure once and forget. Most importantly, you recognize that AI deployments are ecosystems, so your tracking must cover the model service, the application wrapper, the data connectors, and the libraries that handle inputs and outputs. This is not busy work. It is how you keep your security posture from slowly drifting into guesswork. If you can consistently answer what are we running, are we exposed, and what did we do about it, then you are practicing the kind of disciplined vulnerability management that makes AI systems safer in the real world.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.